Hello and welcome to this clip on more advanced titration calculations. This time we're going to be looking at how to work out the number of moles of water crystallization, but using the titration technique. Now you're probably familiar with the idea of simply taking a sample of hydrated salt and heating it until it goes to constant mass by driving the water crystallization off. You weigh it before, you weigh it after, and this tells you the amount of water in grams that it contains. You can also work out the number of moles of water crystallization using titrations. So the idea is that many bases, particularly things like group 1 and group 2 carbonates, exist as crystalline solids. So to exist as a crystalline solid, something should have to have water crystallization attached to it in its ionic lattice, so that the water crystallization molecules allow the crystalline structure to form. So let's look at Na2CO3 as an example. So if we look at one particular version of sodium carbonate, which has 10 molecules of water crystallization per Na2CO3 unit, the Na2CO3 anhydrous, in other words without the water crystallization, that's the part that will react with an acid, and that can be titrated. Whereas the other part, the 10H2O, won't react with an acid, so you can now look at it in terms of which part of the molecule is being titrated in reality and which part of the molecule is being left behind. So we can make use of this to work out the number of moles of water of crystallization. So the key to doing this, to allowing this to be calculated, is to realise that the molar mass of the hydrated base, so in this case it will be the whole thing in front of you, your Na2CO3.10H2O, that can be worked out from the moles that you have found out that react in a titration and the original mass that you weighed out. So moles equals mass over mR, so that can be rearranged. So once you've got the molar mass of the hydrated base, you can take away the molar mass of the anhydrous base, which is just the Na2CO3 bit. You can work that out from the periodic table. And the difference between the two, the MR of water is 18. So how many times does 18 go into that difference? That tells you how many moles of water, and therefore the value of X. So if you're still feeling it's a little bit complicated, and maybe you aren't 100% sure about it, let's go through a worked example. That's probably the easiest way to demonstrate it. So looking at this one, it's important to look at your data and see if you can work out what you have enough data to calculate the number of moles of. So looking at the data, the first thing you come across is 6.43 grams of your sample of hydrated sodium carbonate. Now, what you don't have is the MR of that hydrated sodium carbonate, because you'd need to get the number of moles to work that out, you'd need to do mass over MR, so that's not a good idea to start off with. However, what you do have some information on is H2SO4. You have 19.7 centimeters cubed and you have 0.230 moles per decimeter cubed. So therefore we can use N equals V times C. So let's start off with that. So what I've done is I've divided 19.7 centimeters cubed by 1,000 to conversion to decimeters cubed, then timesed it by 0.230, which is my concentration, which gives me 4.531 times 10 to the minus 3 moles. Notice I've underlined the final answer in that step, so the examiner knows exactly which bit to look at and which bit to credit. The little n before H2SO4 just stands for the number of moles of H2SO4. It's just a common convention that we use. So it's worth pointing out here that the mole ratio I'm actually looking at is sodium carbonate to H2SO4. The XH2O is just along for the ride, so to speak, because it's present in the sodium carbonate, but it's not reacting with the H2SO4, so it's not included in the main equation. So the mole ratio of sodium carbonate is written as sodium carbonate as in its anhydrous form, reacting with H2SO4, so therefore you can assume that the number of moles of Na2CO3 that's reacting is the same as the number of moles of Na2CO3.XH2O. So now we can say that the total number of moles of Na2CO3.XH2O is also 4.351. times 10 to the minus 3, because that was the number of moles of H2SO4 that was present in the first place. So the next thing to do is to work backwards to our original sample of 6.43 grams that was dissolved in 250 centimetres cubed of water. Remembering that we actually only used 25 centimetres cubed of this, which is 1/10, and now we've worked out in step 2 the amount of moles in 1/10 of that sample, then surely all you have to do is multiply the answer to step 2 by 10 to work out the number of moles in our original sample. So there it is, 4.531 times 10 to the minus 2 moles. So the next thing to do is to get the molar mass of our hydrated sodium carbonate. That's relatively easy. You take the number of grams of it, which is 6.43, and you divide it by the number of moles. So I'm rearranging moles equals mass over mR. So this time what we've got to do is mR equals mass over moles, which gives us 141.9 grams per mole to the minus 1. Notice I'm putting in units for mR, which is grams per mole to the minus 1. So we're nearly there. The last thing to do is to try and work out how much of that 141.9 grams per mole to the minus 1 is actually water. So to do that, you take away the mass of the anhydrous salt, the molar mass of the anhydrous salt, does the Na2CO3 bit. So from a periodic table, you can add all that up, and then it gives you a value of 35.9 for XH2O. So finally, by taking the value of the mR of anhydrous sodium carbonate away from 141.9, so 106 subtracted from 141.9, that gives us 35.9 grams per mole, which is the mR of our fictitious .xH2O. So to work out what X would be, because the mR of water is 18, you divide that by 18, and that gives us 2 to the nearest whole number. So the value of X would be 2 in our formula.